This program is brought to you by Stanford University.
Well, thank you, Laura, and thank you for the introduction. It's great to see a big crowd right here. You know, one thing just come to my mind: if we keep having big crowd for the energy seminar for the next 5 to 10 years, this country has a hope to overcome the energy problem. Let's keep doing that. So today I'm going to tell you what I do in my research group, how to design nanomaterials for energy storage for batteries and supercapacitors. I would like to start by thanking a bunch of people. First of all, I get very talented, whole list of talented graduate students right here. So they all contribute to the work to a certain degree, particularly Candice Chen and postdoc Li Feng and Jan and a few other graduate students. I would like to also acknowledge, I have very good collaboration with Professor Bob Huggins. He's the super expert in these areas. Actually, battery expertise spread out from Stanford to other campuses. You perhaps didn't know about that. Also, Professor Riccardo Ruffo, coming from Italy during the summertime, spent half a year in my group. And Professor Dongkyo Kim from Korea also spent some time in my group developing the battery programs. I have a bunch of other collaborators. And also, I would like to thank GSAT for the funding support. This is a really gracious support, a really large amount of support allowed the program to go. Now recently joined by KAUST and ONR to support this work. So I would like to start by several slides of introduction about energy storage. The importance of energy storage, you more or less have day-to-day life examples, mostly in the portable electronics areas. You know about cell phones, laptops, so this relies on batteries, that's energy storage device, to really drive this application going. Looking at the future, what's really important is how to electrify vehicles and have hybrid, plug-in, and electrical vehicles. Since transportation accounts for about 25 to 30% of carbon dioxide emission, so getting vehicles electrified has a significant meaning to the environmental problem, not only just the energy problem. While looking at even bigger scale, you look at larger scale energy storage come together with solar, with wind. These are the renewable energy sources that are not available every time, all the time during the night. You need to come out energy storage to store this energy so you can use it at different times when you really need it. Grid-connected energy storage become more and more important, and GSAT just sent out a proposal call, I believe that was last night or this morning, asking for grid-connected energy storage ideas. So this huge market right there, and connecting with building, of course, is very important as well. These three areas of applications represent different excitement, different scale, but they share a common properties in thinking about energy storage. Let's look at the current technology for store energy. I only list 4 right here, related to how do you store electricity, how do you use electricity. Capacitors, supercapacitors, batteries, and fuel cells. This plot is the power density versus energy density for different technology. Going from capacitors to fuel cell, first of all, the energy density is increased dramatically. And the power drops though, and the capacitors has very high power, but not enough energy density. Now you look at all these important parameters related to energy storage technology, which include energy density, power density, cycle life, and safety, and cost. Depending on which areas of application you are talking about, portable electronics, electrical vehicles, or large-scale energy storage. There's a different emphasis of these parameters. But ideally, you would like to have every parameters to be as high as possible. Of course, cost to be as low as possible. So for most of the audience right here, I see perhaps a lot of undergraduates sitting right here. Let me, let me tell you what we do in the group. But before we do that, let me show you some background slides on the energy storage mechanisms. Let's look at capacitors. In high school physics, you learn about this. Capacitors, they are two parallel plates, metallic plates, come close together, separated by a dielectrics. This is an insulating layer. Well, typically, the thickness you can reduce down to about a micron size also. Not too small, unless you use semiconductor fabrication technology to deposit very thin film. Otherwise, this is not going to be very small. So you have these two metallic plates. You store the energy in form of charges. They stay on the surface interface right here. The energy density is related to the capacitance of your capacitor, and also the voltage you apply to charge up these capacitors. Well, this capacitance value C scale inversely with the thickness of this dielectrics layer. That means, the dielectrics layer, you can only get down to about a micron also. The amount of energy you can store is not that big because you have this thickness to be quite large. Supercapacitors, or say electrochemical capacitors, use different mechanisms to store energy, slightly different, but more or less similar to capacitors. So the idea is, how do you reduce this dielectric thickness down to nanometer scale, about 1,000 times smaller? The idea is you take these two pieces of metals, instead of using dielectrics, now you use electrolyte solution. So it's in, for example, aqueous solution. You have salt dissolved in the aqueous solution, so you have ions in the solution. If you apply a voltage, positive this side, you accumulate negative ions, that's anions on this surface. Cation with positive charge go to the right-hand side electrodes. Now the capacitance of these supercapacitors, the relevant length scale is the separation between the positive charge and negative charge. This is extremely small. The relevant thickness now is so-called double layer thickness. With say 100 millimolar or a molar ionic concentration, this is less than a nanometer also. Looking at the length scale, so you reduce the distance between the charge, positive and negative charge, you increase the capacitance dramatically, and then you can increase the energy you can store dramatically. That's why you see the previous plot right here. Supercapacitors now move to the right-hand side of the plot. Now looking at the batteries. Batteries is can store even more charges. Capacitors and supercapacitor relies on surface to store a charge. Now battery relies on the whole bulk of the materials. You put all these metal ions into the crystalline lattice of these electrodes. And I use negative charge on the other side. Indeed, in the battery case, you don't see this positive charge and negative charge. You see the oxidation state change within the materials inside the battery electrodes. This can store even more energy. At the end, the difference you see is this is capacitors and supercapacitors is surface storage, and batteries is a bulk storage. That's why batteries store a lot more energy. Now, next question is, look at the title of this talk, design nanomaterials to impact this energy storage. Now, what exactly nanotechnology can do? Why nanomaterials can help energy storage? Now, let's look at battery case first. To get these metal ions into the bulk of the electrodes. So they need to diffuse a long distance, if this is a big piece, to go into the electrode. So you don't like it. It's going to be slow. The way to improve it, if you make this electrode, this big piece, into tiny particles, So each of these particles contact with the electrolyte. Now the metal ion going in rate can be speed up very fast. The distance required this ion to go in becomes very small. So and by doing this way, you can improve the speed, the power of your devices. Of course, these particles need to stick onto a metallic collector. So I use this to indicate this is a metal collector. So what about this? Instead of using particles, let's use another format of nanostructure, such as a so-called nanowire. This is a wire shape. The benefit you gain, not only you reduce the distance, the ions going into the battery materials, at the same time, you compare with the particles, to really use the batteries, you not only need to move ions, you also need to move electrons. So in this case, electron needs to shift from the metal electron going into the particles. This needs to hop because between particles, there's a particle resistance right there at the interface. So it's not that efficient. Now you go to nanowires. This is like a highway, it just goes in very fast. Well, it looks like you can use the nanowires to improve both ionic conductivity and electronic conductivity. The story holds the same for supercapacitors. For supercapacitors case, if you go from metals, big piece of metals, now to these small size particles now going into the nanowire, you gain the same advantage. You speed up the electronic conductivity, you speed up the ionic conductivity. So that has been the idea, general ideas we have been thinking about in our research group. Not talking about the detailed materials yet. This is the common benefit you can gain by using a nanomaterials, efficient electron transport, and a large surface area for a large ion flux to increase the ionic conductivity. So now speaking of nanowires, we are going to focus on nanowires now. In the last about 10 years or so, there's a lot of development in the nanowire areas. I give several examples as a background coming from leading research group, Lieber Group, Samuelson Group, and Pei-Dong Yang Group at Berkeley. And in the early day of nanowire development, a lot of attention is focused on making faster and faster transistors, and later move on to sensors, chemical and biological sensors based on the field effect. When I was still a graduate student, this is my own work with Lieber. And how to use this nanowire to move photons around. So there's a nanoscale photonics area, really big areas now. And how to use this nanostructure for solar cells, nanogenerators for energy conversion. There's also significant effort at Stanford campus right here. I give a list of a research group having a nanowire research program on this campus, ranging from material science to electrical engineering, chemistry, and mechanical engineering. So you can name it. So it's a really exciting effort on this campus. In my own research group, the focus has been how do we really think about tailored nanomaterials for energy applications, also for other applications. So we figure out how to control the shape. In this case, this is a nanowire with the branch structure coming out, and these beautiful helical branches by controlling the growth condition. You can form a really nice ribbon. You can make these vertical pillars. This is not only pillars, this is a cone-shaped structure. You can make this a helical structure as well. You can control it to certain degrees now. So my research program has been how do we use these materials and design them very well for energy storage, solar cells, memories, and bioprobe. So today I'm going to only tell you the one area, that's energy storage. Now let's look at the first example. There's two outlines right here. Somehow the slide doesn't. So I'm going to tell you a first area related to batteries. But let me mention how we made these nanomaterials. Mention it a little bit so you have some background. The way we made these materials, this is the material we would like to make into nanowire. We heat up the furnace and vaporize this material, carry gas coming down, and take it to the downstream. This is a little bit lower temperature with this nanoparticle catalyst, metallic catalyst on the surface. This nanoscale catalyst functions as a really good solvent above a certain temperature to dissolve these materials from vapor phase going into liquid phase. After supersaturation, they nucleate and grow into this one-dimensional nanowire structure. Now let me show you the first example on the nanowire lithium-ion batteries areas. So we care about lithium-ion batteries, among all the battery technology, is because it produced the highest performance so far in terms of the energy density per unit volume or per unit weight, much better than nickel metal hydride, nickel cadmium, and lead acid batteries. But you look at what's really the problem related to lithium-ion batteries. Now let's look at the 101 of batteries related to lithium ions. Lithium-ion batteries have two electrodes. One electrode is carbon, that's negative electrode. The other electrode is transition metal oxide as a positive electrode. So you have a current collector right here to collect the charge carriers. The real battery really looks like a jelly roll. So this current collector is a thin foil. You can roll them up into the battery. This is a top view with maybe like a meter long of a tape. And this is how they look. It's a cylinder cells. The most critical parameters now related to batteries, particularly towards electrical vehicles application, is the energy density. That is determined by how many lithium ions you can store in this battery electrode, what's the voltage, the potential difference between negative and positive electrodes. And this is, you have a per unit volume or per unit weight parameter right there. Looking at all these battery materials working so far, anode, that's negative electrode, is dominated by carbon. It can store the number of charge, that's 370 milliamp hour per gram. So just forget about the unit. This is conventional unit. Just remember this number a little bit. And the cathode materials is more or less a lithium cobalt oxide or lithium manganese oxide spinner or lithium iron phosphate. Among this big family of the materials, they more or less have the similar energy density as well, a similar charge storage capacity. That is also why, with only these four materials, they really dominate the market. And you look at Japanese company, Korean company, and Chinese company, they all use these materials for batteries. Look at the batteries performance, lithium-ion battery performance, and the energy density, green curve and the red curve. Since 1991, Sony commercialized the first lithium-ion batteries. Is about 18 years now. The batteries improvement is not that big. On the average, it's only 8% per year or so. That's very, very unaggressive. And this improvement indeed is not due to new materials improvement. It's more or less due to better and better packaging. But you cannot do this forever. That's why recent years you see saturation of energy density per unit volume or per unit weight. If you look at it 2008 compared with 2007, there's no improvement at all. So clearly new materials are needed to develop better batteries. So my group has been looking into the future generation of materials which are different from the previous generation. In a sense, the new materials can store a lot more lithium ions, but they have the drawback that is the large structure change and volume expansion. And lithium ions moving rate can be slow. This is exactly the ideal system for designing nanomaterials to overcome those problems. So, I mentioned to you, nanomaterials in general have two advantages. One is the shorter lithium diffusion distance, so lithium can come in into the center of the material very fast. And second is very efficient electron transport. For the materials which can store a lot of lithium, you gain one more advantage. That is when you have large structure change and volume expansion, they don't break. For example, you take a nanowire growing up from a metallic substrate surface, lithium ion comes in, they expand, but they don't break because each of these nanowires are small enough to take this, the strain induced by the structure change. One example is silicon. Silicon has been looked at for many years, and did Professor Bob Huggins right here. Look at this material perhaps 30 years ago, before maybe even before I was born. Compare with carbon, and silicon provide extremely high energy density, charge storage capacities. But the problem is the volume expansion. So when something expands by 300%, it's going to break, unless it's nanomaterials. And you might want to ask why nanomaterials don't break. I have told a lot of people this story. If you don't have any mechanical background, the idea is you take a piece of very brittle silicon wafer, you just smash it, then you produce silicon dust. And those silicon dust, more or less in the size scale of a micron scale. Now we made our nanowires. They are already smaller than a micron scale, so you cannot break nanowires anymore. They're smaller than the smallest things you can break. So we use this method, the catalytic method, using metallic particles under the CVD growth condition, and grow this nanowire directly out of metallic substrate. You really gain the advantage. The bonding right here is chemical bonding, very, very strong. So you don't need to use any binder to hold this nanowire together. You don't need to use a conducting carbon to help the conduction, because electron transport is so efficient within the nanowires. These are the nanowires you get, typically about 100 nanometer diameter also. These are the battery cells we made. What we do is we take the nanowires on the metallic electrodes, and then there's a counter electrode. To test the nanowire electrode, we use lithium foil as the counter. And we press them together, and between we have an insulator, a separator right there to prevent shorting. But this separator, they are porous, allow you to put in an electrolyte, so lithium ion can conduct in between the two electrodes. This is the potential curve you measure. You monitor the voltage versus capacities. So you give a constant current, you monitor its potential. As soon as you put in lithium ions, the potential drops close to zero. But let me remind you, we are doing this measurement versus lithium metal electrode. So this doesn't mean when you use silicon nanowire for the batteries combined with cathode material, the voltage is zero. If it's zero, you don't gain any energy. This is only half of the cell to allow us to evaluate silicon nanowires. So potential show a plateau, and you discharge this and charge it again. So this allows you to calculate the capacity. In very early days, this is almost the first set of data we produce. We can go up to extremely high charge storage capacity for multiple cycles. Now, this is silicon nanowires. This line right here is carbon. So we produce about 10 times of the carbon charge storage capacity. That has been very exciting. Now the question you ask is, you use this nanowire, whether you can produce high enough power density, high enough current density to power your iPhone, for example. So we have done the rate dependence charging, discharging, C/20 right here. This is the battery terminology, means 20 hours charging and discharging. And once is 1 hour. And the 1 hour charging, discharging, this is a percentage advantage over carbon. You can still have the capacity 500% more than carbon. So that's very exciting. And the 1C right around here, you are really approaching the current density, allow you to do your laptop and cell phone charging, discharging. Well, how many cycles we can run now? Well, it looks like this nanowire, they are robust enough, allow us to go for many, many cycles. And, but we didn't push nanowire that hard. If anything you push them very hard, you want to charge 4,000 milliamp, that's their full capacity. Well, you are going to break them after tens of cycles. So we decided to try about 1,000. 1,000 already 3 times of carbon. Well, you can run for close to 200 cycles with a very, very little fading of capacity. You keep 95% of capacity. So what about the breaking problem? Breaking has been the biggest problem for silicon. So after we do battery charging, we look at how the nanowires look like under scanning electron microscope. This is before lithium coming in. This is after multiple time of charging and discharging. One information you get out is nanowire, they don't break. They still look like nanowire. And second thing is their diameter becomes bigger. They become fatter, but they still don't break. So that's a good news. This is consistent with what we are thinking. We have done a lot of detailed studies to look at structural change, to look at what's happening in the interface, but I'm not going into the detail of that. Let me just show you the most important thing you see in the silicon. Use that for batteries electrode. That is the structural transformation process. The nanowire we make after we do the synthesis, they're single crystal nanowires. And you look at this under transmission electron microscope. This is a crystalline lattice. You can see it's a single crystals. Electron diffraction shows this spot pattern. That tells you it's single crystals. And with some lithium coming in, part of nanowire now become amorphous, and part of a nanowire is still single crystalline. So this is amorphous silicon with lithium in it. And after you put more and more lithium in, now crystalline nanowire become almost completely amorphous, leaving behind this dot. That's a tiny, tiny crystalline of silicon. At the end, these nanowires completely become amorphous after you do you get lithium in, a lot of lithium in. They become amorphous completely. Our detailed study have shown this is really the picture happening. During the first cycle, when you charge lithium into silicon, it goes through this transformation going from crystalline to amorphous through this different stage. Now if you take out lithiums, so you start with this amorphous silicon with lithium in it. Now you take out lithium, and more or less this silicon nanowire, they shrink a little bit, but not completely back to the original crystalline structure. This is still quite big. If you do multiple cycles, this size can increase a little bit more, maybe approaching to this size after you do multiple cycles. So now the key information I would like you to get is this crystalline phase involved, this amorphous phase involved. Now you go back and look at our potential curve. When you charge up your batteries, during the first charge cycles, so you need to go down to low potential to charge lithium into silicon. When you get to right here, they all become amorphous. Now you take lithium out. You come to the second cycle, you charge it again. And you start with amorphous silicon nanowire from here, start to put lithium in. Now you start to see this potential value you need to have to charge up lithium, to charge lithium into amorphous silicon. It's different from the potential you charge lithium into crystalline silicon. So it is different between amorphous and crystalline. Well, that really activates our mind. Well, we keep thinking whether it's a good idea to you make a nanowires with a single crystal core, and then you have an amorphous shell. And when you charge out your batteries, you only charge the amorphous phase because you can control this voltage potential, allow you only charge out the amorphous phase, leaving this single crystal core right there without any change. So you have this single crystal core function as a mechanical backbone, efficient electron transport pathway, allow you to run many, many cycles without breaking, and allow you to do extremely fast charging and discharging. That would be extremely important for the electrical vehicles, for example. So we decided to test this idea, and when we charge up the batteries, we only charge up to this potential if we can make amorphous and a crystalline shell and core nanowires. So we decided to do it. We made a single crystal nanowire by also this nanoparticle catalyzed growth. After that, we changed the growth condition a little bit, allow you to deposit amorphous silicon indicated by the red color on the surface of the single crystal core. So we have done extensive study to show you, this is single crystalline nanowires in the core. These are the amorphous shell. Now you look at the size scale. Your single crystal nanowires, when we make them, we can make them in about diameter about 20 nanometer also. When you coat the amorphous silicon shell, this thickness right here can go up to 100 nanometer or bigger. Now you calculate the single crystal core volume only accounts for about 2% of the total volume. It's also about 2% of the total weight. So by using this idea, you are not really wasting weight because you never use a single crystal core. So you worry about maybe you waste this weight or volume for the batteries. Indeed, you are not wasting much, only 2%. But the payback you gain is huge. This is the cycling data, capacity versus cycle number. This we run for 100 cycles. We run extremely fast rate, only use 7 minutes to charge up your battery and discharge your batteries. Since we limited our potential for charging, so we are not going to reach, say, 3,000 or 4,000 milliamp per gram of capacity. That's very high. We perhaps only reach close to 1,000 also, but that's good enough. This is 3 times of carbon. That's very high. What you gain is you get extremely fast charging discharging rate, and also your lifetime becomes extremely long. Within 100 cycles, you really don't see any decay. So that's really the fundamental ideas within my group. How do you design your nanomaterials for energy applications? Combining all these factors together, combining the expertise we have in the nanosynthesis to create new materials to provide a better performance. So to compare, if you limit the charging potential to about 150 milliwatt, you don't go below that. After tens of cycles, you can see this crystalline core still inside. So maintain as a mechanical support, electrical support to allow you to do extremely fast charging, discharging. And if you charge out your battery, this core shell nanowire using very low potential, after you charge it once, the whole nanowire becomes amorphous. You don't see this crystalline core anymore. Well, that is consistent with our ideas. We can maintain this crystalline core by limit the charging potential. Let me summarize a little bit research related to silicon. So we briefly solved the biggest problem. That's the mechanical breaking problem by using nanowire structures. Let me also emphasize the importance of silicon. Silicon is so abundant, so anything you can do on silicon will be great. But everyone will be asking you, well, there's not enough silicon in the world, but those are referred to solar-grade silicon, high-purity silicon. And for batteries, you don't really need to use high purity. Metallurgical grade is good enough. It's like maybe $100 per ton price, so it's extremely cheap. This mature semiconductor manufacturing process allows you to think about manufacturing of the nanowire for the battery. So that's a good news, particularly for Silicon Valley. What about the safety? Giving silicon can store so much energy in it, so many lithium ions in it. So safety will be a concern. But let me tell you, something. This is speculation only, so there's no experimental data yet. So silicon, when you charge lithium into silicon, the potential is higher than lithium metals by about 100 milliwatt or 200 milliwatt also. Well, if you use carbon, that is in the existing technology, that's really close to 0 watt compared with lithium metals. So carbon has this well-known problem, lithium dendrite formation if you charge your batteries. When lithium dendrite is formed, that causes shorting, that causes explosion of the batteries later. Particularly in the cold weather, so lithium dendrite can be formed even easier if you overcharge it. Now you have this potential slightly higher than lithium metals. That allow you, when you use silicon, that allow you to prevent this problem, the lithium dendrite formation problem. And the second thing is just by thinking about the electrode itself, a battery electrode. When silicon burns, what does it produce? Some chemists right here. It produces glass, also sand, or silicon dioxide. When carbon burns, it produces what? Greenhouse gas. It's gas, so it's going to explode. This is by thinking about the electrode itself. Of course, you have organic electrolyte inside. That's the most dangerous part. It's not the electrode. But this is fun to compare. Well, our research didn't stop right here. So when you look into what's happening in silicon nanowires, this is the overall picture. You take a crystalline silicon nanowire, you push lithium in, they become amorphous. You take lithium out, they stay at amorphous. So you're cycling your amorphous phase. This is your amorphous nanowire. They look bigger than your crystalline nanowires. So that allows you to think, is this only the amorphous phase? They look bigger, so much bigger than crystalline. There got to be some nanopores inside. So the real picture is like this. You have a lot of porous structure within silicon. Well, this is really, really exciting. This is a process allow you to use electrochemical cycling to create nanopores, come out a new set of the new materials to think about other application. So let me remind you the supercapacitors again. So I said using nanowire can be beneficial for supercapacitors because you increase the surface areas, you have efficient electron transport. Now having these nanoporous nanowires for supercapacitors is going to be even better. Now you have a lot of these pores. This create additional surface areas to increase your capacitance and to increase your energy density of supercapacitors. And at the same time, they are well connected. All these materials are well connected, so they are still provide efficient electron transport pathway. So we decided to explore this idea. But let's look at the structure a little bit. This is a single crystal silicon nanowire. This is after one lithium-ion cycling. So you push lithium in, you take lithium out. You go look at them under a transmission electron microscope. Well, this is single crystal. You see the lattice plane. This look like become amorphous now, but you don't see a lot of feature yet because the pore size are so small. So it's not really that visible on the transmission electron microscope. But after 5 lithium-ion cycling, you see the roughness becomes more. Well, this allows you to believe, maybe they're really pores inside, but you cannot resolve them clearly because you have a lot of pores. Your electron beam coming down, go through so many pores. So this average out, but more or less the roughness becomes larger. So this gives you some indication. You might have nanopore right there. So we have study the porosity of this nanowire after cycling by doing the gas absorption measurement. So I'm not going to go into this data. Let me just tell you what we found. So the overall finding is this is the size of the pore. This is distribution, the number of the pores, for example. And let's zoom in, just look at these areas that's on the right-hand side. After one lithium-ion cycle, you get lithium in, you take lithium out, you create pore. The pore size has a distribution about, say, 3 nanometer or so. Very, very small pore. And then you can do multiple cycling. You can do 3 cycle, 5 cycle. It looks like the size of the pore shift to the right-hand side, so become bigger and bigger. Well, this is fascinating to me. This is the way you can use electrochemical cycling, depending how you do it, how many cycles you do. You can control the pore size, allow you to tune materials property designed for supercapacitors. So we have done supercapacitors measurement and figure out the capacitance, surface capacitance. When you do multiple lithium-ion battery cycling, you create pore, and then you do supercapacitors measurement. It really increases with multiple cycling, so you increase the surface areas accessible to those ions and the electrolyte. Now let me tell you the overall conclusion we found. This is the energy density and power density. I apologize for the different plots. So I use a power density along this axis and energy density. And my postdoc gave me this slide and just reverse the order. But more or less, the parameters you are looking for is you would like to move everything to the right and to the top and to improve your performance. This circle indicating nowadays the things you can do, the current technology can do, the state-of-the-art technology can do in terms of the energy density and power density. Silicon nanowire, when used as supercapacitors electrodes, use an organic electrolyte, will allow you to increase the electrochemical supercapacitor energy density by 10 times now. So we show that, so we can beat any other peoples in the world in terms of this energy density. And the power density is more or less similar to the existing supercapacitors. So that's very exciting. This again comes back to the fundamental idea. How do you design your materials right, control the length scale right, control the morphology right, to have a better performance for the energy storage? So there's some more new development in the groups. A lot of phenomena we are looking at, for example, you look at silicon. It goes from crystalline phase to amorphous phase, and involving dramatic structure transformation. You've got to understand that. So we are developing new tools to really allow us to observe this transformation in real time with the nanometer angstrom scale spatial resolution. We are also developing well-defined samples to even look at this phenomenon more clearly. I'm going to show you what I mean in a couple of slides. But now, let's look at the new technique we are developing in the group. Now we are trying to combine transmission electron microscope that has the spatial resolution about angstrom scale with electrical chemical measurement. That's your battery measurement. You would like to do your battery measurement inside transmission electron microscope. That's TEM. So we call it in situ study. My graduate student David Xiong, Stefan Master, and postdoc Hailin, they have been developing this technique over the last 2 years. And here's the device we made. This has a really thin silicon nitride membrane, really transparent to the high energy electron beam, about 50 nanometer also. We made our nanowire device on top of this membrane. So you can throw down a nanowire and then you make multiple electrical contact. We haven't been able to do battery measurement yet, but we have the data related to phase transformation for other projects and memory. I'm going to show you, to give you the example, what kind of things are you expecting. These are the device we made. This is a nanowire, single nanowire contacted by multiple electrodes. So soon enough, we are going to put down electrolyte and counter electrode. We would like to do in situ battery measurement. But now let me show you the examples we have for the another project, phase change memory. In the phase change memory case, there's a crystalline to amorphous phase transformation as well. We would like to apply electrical current to do jaw heating to heat up the nanowire above its melting point and see what happens. So this allows you to do a memory, change it from crystalline to amorphous, amorphous to crystalline. Well, for a while, a lot of people think, this is a simple memory mechanism, crystalline to amorphous, amorphous to crystalline. So now we can watch this in real time on the transmission electron microscope. Well, a lot of other things happen other than crystalline and amorphous transformation. So this is a nanowire coated by encapsulated by layers. Now it passes current through it, it's going to melt. Size is about 100, 200 nanometer or so. You start to see materials moving around like crazy, forming this nanotube structure. It's hollow. So you see this IV curve, current really go like crazy. So we hope to use this similar type of technique to do our silicon nanowire battery measurement and also do other materials battery measurement, allow you to watch this in real time and really understand and also control your materials property better. So we are interested in new well-defined samples. Well, this was the TM picture I just showed you, 10, 20 slides ago. So we made this nanowire. They are randomly oriented. Nothing wrong with this nanowire. They are nanowire usable for batteries. But for fundamental understanding, giving a certain amount of lithium going in, you want to see how much volume change you have, and you would like to see whether there's a breaking at the interface between nanowire and the metal electrode. Well, that's harder to do. This looks very messy. So what we like to have is this type of pillar. So each nanowire you can watch clearly. You make them into the same size. So that motivates us to develop the technique to make this nano pillar. But the story I'm going to tell you is, as soon as we get this pillar, some other exciting things happen. This is always, how the science develop. You think about some other things. It turned out this structure is very good for solar cells. So the way we made this structure, we produce these silicon dioxide nanoparticles. We functionalize the surface and float them onto water surface, form a monolayer. So you compress these particles, they form close-packed monolayer. Now you did a substrate. This can be a silicon substrate into this solution. And you just put it out, you get a monolayer of particles on the surface of this substrate. This is how they look like. This is 4-inch wafer. You look at everywhere on the substrate surface, you always see a nice monolayer of particles. So if you use that as etch mask, you can etch this very nice pillar. Depending on how you do it, you can etch the different size, different spacing, and you can even control the shape, going from a pillar become a cone. That looks fairly interesting. Well, this is on single crystal silicon. And then one of my graduate students, Jia Zhu, he said, well, let's look at amorphous silicon. So he can etch the amorphous silicon also to form similar type of structure is a nano cone. But what's exciting is just by eyes, you see something dramatic happen. So this really motivates us to go into the area using this structure for solar cells. This is a nano cone. They look like black. You would like your solar cell look like black. They don't reflect light. They absorb all the light. And this is just a vertical pillar, no cone shape, just vertical. They are gray. If it's a film, the same thickness, they look like only gray. So this is very good for solar cells. The reason this is they can reflect so less light is because the so-called refractive index matching. Having the cone right there, light comes in and see the tip of the cone and going into your cone-shaped structure. And the refractive index gradually change from air to your amorphous silicon. It's not like step function change if light comes into amorphous silicon film. Refractive index right here is 1, right here is 4. So it's a dramatic change, and light gets refracted back. But in this case, light just can get completely trapped in and get absorbed. So we have done very detailed measurement. This is collaboration with Xianghui Fan and Michael McGee. Well, we haven't gone to the point yet to do battery measurement using this pillar, but soon we will be able to show that. Well, I think at the end, I want to conclude my slide and leaving time for discussion. And I would like to thank graduate students again and postdoc and my collaborators and all this funding support, and thank you for your attention.
Can you talk a little bit more about the life of the batteries? A lot of lithium-ion batteries are doing 2,000-3,000 cycles now, which is really what's needed for electric vehicles. You mentioned 100, and can you talk a little bit more about what you expect life to be?
Yes, for electrical vehicles, you would like to go to 5,000 or higher. So we are not there yet. There's a lot of understanding, a lot of study needed to really study the interface between nanowire and the electrolyte, organic electrolyte. That interface is very, very important to determine your cycle life. There's a side chemical reaction can taking place. Each time you degrade a little bit, just 0.1%. That's enough to keep your battery cycle only within several hundred. For 5,000 cycle, your efficiency, charge in, charge out efficiency has to be 99.999, something like that percentage. Yeah.
Can you talk a bit about what kind of research, more additional research is needed to get to the point where you can always use it in electrical vehicles? And do you have a prediction on the time?
So there's a multi-level research. One thing is what I just mentioned, study the interface. People call it SEI in the battery community. And also you need to come up with the idea, how do you do manufacturing? How do you roll up this battery foil and without breaking the nanowires? There's a lot of details. You need to figure that out. I'm not the expert on that, and this relies on the company to take this one step further. In terms of the time, it's always hard to predict when will that happen. But giving past experience And a typical materials-oriented technology, when it goes to market, well, it's 5 years, 7 years time scale. It's not like computer science company. It can be 4 years. So 5 to 7 years is more realistic.
You didn't talk about the cathode much, but if you nanostructure the cathode, are you concerned that the increased reactivity might increase the dendrite growth?
Actually, no, yeah. So as I said, silicon is actually better, for many reasons to decrease the dendrite growth. Higher charge storage capacity doesn't mean the dendrite growth probability is increased. For cathode side, we did have some study. Professor Kim is right here, and we have a nice collaboration on lithium manganese oxide. I didn't have time to talk about this, so we are working on that as well, how to improve the energy density, safety, cost, and everything about cathode. Yeah.
We had 3 weeks ago, we again had a very large recall because of explosions caused in lithium-ion battery, and this is the first year the lithium-ion batteries have gone up in price.
Yes. Well, there's multiple reasons behind the recall. In the manufacturing, you use this metallic foil, and if this metallic foil during the process, you have a dust, metallic dust right there, you can cause shorting as well. And for Sony's case, people think it's because when you do laser sealing of your battery can that produce metallic dust, that can cause shorting. A little bit of shorting is enough to heat up the battery to cause bad things happen, propagate, and exponentially.
Could you talk about the potential cost per kilowatt hour when these things are developed?
Not yet. So this is still too early to estimate that. There's multiple parameters coming in to estimate those costs. Well, at least good thing about silicon is it's going to be very cheap in terms of materials cost. Process cost, maybe you need to learn something from how people make amorphous silicon solar cell, the roll-to-roll process. But I don't have the parameters to give you the cost estimation.
So I don't have the details. I read somewhere very quickly about a company in New Jersey called M-Phase that's come out with a nanotechnology battery. Can you talk about that? Is that?
Yeah, I don't know about this company. Yeah.
More questions? Okay, then let's thank you, Professor.
Thank you.
Energy.